conclude the day with Multiphase and low-phase separation.
Thank you, Christina. So, just to explain the title slightly, there's sort of two mini talks here glued together rather inelegantly. So, nucleation and hyperuniformity are not directly related to each other. And the model I'll be using is the one which Cesare described yesterday in the same time slot. So I will recap that briefly. So active model B plus, a model of diffusive phase separation. The title of this workshop includes flows. I will just mention the case with the coupling to a fluid flow at the very end if I have time, but I have nothing much to report on that. So I'll talk about diffusive phase separation, and the two stories I want to tell. One is nucleation, which is when you have a free energy in equilibrium, when you have a free energy barrier to get from a homogeneous to a phase-separated state. You have to go through a critical nucleus of a certain size. And we'll see that that is still true in the active model B plus for phase separation without a free energy as such, but we'll see that the same mathematical structure survives. And then the second story is to do with the late stage coarsening behavior. So once you've nucleated droplets or go through a spinodal decomposition, you have a coarsening process for blobs of material of two coexisting densities. And this is has a well-known scaling regime, which I won't talk much about. There's a length scale which progressively gets bigger with time. The one thing I want to focus about that regime is the low Q behavior, so the very long wavelength behavior at a scale much bigger than that coarsening length, where you have this thing called uniformity, which says that the static structure factor is suppressed and in fact goes to zero, and what's more, in these systems it goes to zero with the power of Q to the fourth rather than Q squared, which might be the obvious expectation if S is analytic and vanishes at the origin, for instance. And the reason for that we can connect with a hidden conservation law, which I will tell you about, which has been lurking in the literature actually for decades, but I only learned about it around 6 months ago, a bit longer. And as I say, if I have time, I'll say a little bit about coupling to a fluid in that setting at the end. So I want to thank my co-authors, firstly Cesare, who was here and spoke the other day, Filippo De Luca, Jiao Ma, Cesare, and myself for the coarsening part. Right. Diffusive phase separation. Okay, so let me tell you about this, starting with the equilibrium case. So many of you will be very bored with these equations by now. This is model B. So phi is a scalar describing the composition in a mixture of two fluids. And if that's a conserved quantity, so its rate of change must be the divergence of a current or a flux. And then in an equilibrium system, the current is some mobility, which I've set to 1, times the gradient of a chemical potential, which is the derivative of a free energy here. And there's a noise term, which is carefully constructed to make sure that this model is an equilibrium model in the sense that if I wait for it to achieve a steady state, I have detailed balance. Any movie that I might make looks the same running forwards and backwards in the stationary state. So the usual choice for the underlying free energy functional here is the phi4 form. So I have negative A, which gives me two minima. So these two compositions here, one positive, one negative, just by convention, are going to be the two coexisting phases. And then there's a square gradient term which tells me that there is some free energy cost of creating an interface. The interface does not want to be too sharp between those two coexisting phases. And the mu, I shall refer to this functional derivative, is in this context called the chemical potential. And the condition for phase equilibrium in general is that I draw a common tangent here, and in this case where the free energy is symmetric, that's degenerate, it's just a horizontal line. And the idea is that in equilibrium the free energy of any homogeneous phase between these two minima can be dropped onto that horizontal line by phase separation. And so in the phase separated state, the chemical potentials are equal, and these are two bulk states, so when I calculate this, I just get the derivative of that function. There's no gradient term in big bulk states. And also the fact that these two tangents meet on the axis here is the same as saying that the two pressures are equal in the coexisting phases, where this is the usual thermodynamic expression for the pressure. And in the region of negative curvature here, between the two spinodals, you have a local instability, and the thing goes from homogeneous to phase separated spontaneously. If you're in a positive curvature region, so say near this minimum, for example, then you have to create a small amount of the other phase. That involves getting over a free-energy barrier in configuration space. Right. So we spent a lot of time activizing this theory. So, and the whole theory is based on the idea of a simultaneous expansion in the concentration field and its derivatives, and working then to the lowest order at which anything different from these blue equations can arise, you find two active terms here. This one is normally written slightly differently. What I've done here is absorbed part of this term into there. So that lambda hat is Cesari's lambda minus zeta over 2. Zeta is the coefficient of this now quite complicated expression. The advantage of writing it this way is that object vanishes in one dimension. And that's enough to tell me that this term here, if I have an interfacial profile phi, cares about the curvature of the interface laterally. It doesn't care about anything I can do in the normal direction, which is a good reason to sort of separate that out and absorb zeta over 2 into lambda here. So these are the two minimal terms that spoil that picture I painted of the system once it's reached a steady state, having forward and backward movies looking the same. And as Cesare mentioned, there are ways of connecting this top-down coarse-grained model to microscopic models by coarse-graining, but I won't say more about that now. So that's called B+, and the reason it's got a plus is because we forgot about this term at the first incarnation. Okay, now a mathematical trick, which will matter to us, is as far as the phi dynamics is concerned, notice that this term here has a curl in general, but the curl is invisible for phi dot because I take the div of j. So then if I'm not interested in the curly part of j, I can think of it as a gradient flow, effectively, but in other words, I can add something to the chemical potential to soak up this zeta term here, but it's non-local. It's basically a Helmholtz decomposition, so I have to find the divergence of this and then take the inverse Laplacian of that. So do a Coulomb integral on, so the divergence of this is like a charge. This is like the potential of that charge. So this charge is Q, and this is its potential, which now is a term that lives in the chemical potential. So you might think, well, why do you do that? Well, this, as I said, is something which relates directly to the curvature of an interface. And if you think of this calculation of this part of the chemical potential, it's just like calculating the Coulomb potential of a charge density which consists of a layer of dipoles whose intensity is proportional to interfacial curvature. So for a flat interface, I get no contribution here. If the interface curves, it's as if I've got a layer of dipoles living on the interface. And the way you can see that is you can look at this object here. It vanishes on both sides. The interface has wiggles as I go across the interface. Its first integral is 0. So I get this strange non-local term into what would normally be a local chemical potential. So that's one way of thinking about why this term is so weird and why it is able to change the dynamics of the theory in a way that this term, although it has effects, cannot do. So if I think about bulk phase coexistence, where interfaces are flat, I can forget about that complicated non-local bit. And in such a phase coexistence, there's no current on average from the dense phase to the dilute or the other. And what you find is you still have the lambda term, or lambda hat term, and compared to the usual common tangent construction, which is to draw the horizontal line across here, these densities get shifted. And they get shifted into a new construction, which we call the uncommon tangent construction. So I changed phi 1 and phi 2, and therefore I changed the difference between them, by an amount which depends directly on the lambda hat, first active term. And that looks like a pressure mismatch between the two phases. So one of the things which is difficult in thinking and talking about this model is it's quite abstract. It's difficult to connect statements like that to, you know, thinking about particles and pressure and mechanics and so on. But an alternative statement is that that activity, the lambda hat activity, has the effect of pumping stuff across the interface between phases. So by the time that's finished, the two densities which I thought were coexisting have shifted so that there's a current backwards against the, what would be the equilibrium part of the current to restore balance. And this kind of weird shift in phase equilibria is something which is seen in a slightly different language and a slightly different setting in active particle models as well. So there's some real physics behind this. So something I'm just going to need later is if I am sitting just to the right of that previous tangency point, so this is epsilon is the supersaturation, it's the amount by which the composition variable or the density is away from the equilibrium point, then I draw the tangent there, and this big green arrow here is telling me in an equilibrium model how much free energy I can gain per unit volume or in making some of this new phase over here. So that epsilon is the supersaturation. This is the driving force, and you'll see this expression, epsilon second derivative at phi 1 times this gap, which is just the geometric way of calculating the length of that line there. This object will occur several times in the coming slides. Okay. Any questions about that? Right. So as Cesare already indicated, interesting things happen, particularly with the zeta term at curved interfaces. This is also the way in which diffusive equilibrium is established once I have some droplets or some kind of spinodal pattern, how I get from there to the finished structure, as it were. So across, and I shall now talk about phi 1, which is the negative phi, as a vapor, and phi 2 as a liquid, and that would be a perfectly legitimate setting. And in a curved interface, these get shifted at the in the vicinity of the interface. The normal way of saying that in the passive case is that the chemical potential in the vicinity of the interface is lifted by an amount proportional to the interfacial tension, inverse of the miscibility gap, and K here is the curvature, so it's the mean curvature. So if I just have a cylinder, that radius is 1 over K. So, and these two deltas are both shifted by an amount proportional to this, and this object here. And so the key thing then is you have then the scope for tension-driven diffusive flows. And in the active case, as again Cesare said, all that you have to do to calculate the little excess vapor pressure, if you like, outside the liquid droplet, which depends on the curvature, is to subsume the physics of that zeta parameter, which is quite complicated, but the way it shows up is as a non-equilibrium interfacial tension in an otherwise identical expression. So a lot of rather complicated activity physics can be absorbed into that. And so I can take both of the active terms, and in this context of this problem of finding out the excess vapor pressure in a curved interface, they both look like a small or large change in interfacial tension, with this added twist that this has a different value on the two sides of this interface. So because of that layer of dipoles that I talked about here, delta 1 and delta 2 are disconnected from each other. And it means that the effect on the vapor outside a liquid droplet and the effect of the liquid outside a vapor bubble are not the same, and that shows up as two different values of this tension. And the other thing, as Cesare said, is that one of these only can become negative, but I won't be talking about that case today. Okay, so the point then is that if I have some droplets, this little excess amount of density in the vapor, which depends on the curvature, is what drives the growth of large droplets and the shrinkage of small ones in what is called the Ostwald process. So just to say a little bit more about that, what I'm going to do then is I have a problem outside. I have a droplet. Look, think of the behavior of the excess concentration in the exterior domain, and let's suppose that at infinity this is epsilon. So I set it to be some supersaturation far away from my liquid droplet, and at R plus it is this delta 1 which is fixed by the curvature, and then I have a quasi-static problem, which means that I have effectively to solve Laplace's equation in the external region, and then the gradient of phi will tell me the flux, the rate, which is the rate of evaporation or deposition onto this liquid droplet here. So you can think, if you want to think of, in the equilibrium case, just think of supersaturated vapor, so steam, and a droplet, a raindrop forms in it. And this is the expression I said before. In general, for a spherical droplet, I have d minus 1 over r here, because that's the mean curvature. Right. So, solve Laplace's equation, calculate the current at the surface, which is the gradient of this excess density here, and that tells me the rate of change of, well, the speed of this interface up to a factor delta phi. So the jump in density across the interface times its velocity is equal to the current onto it, and that's the gradient, as I said. So you get an equation for the rate of change of the radius of this droplet as a function of its size, and in it lives the chemical potential and this delta 1, which has a 1 over r here, the supersaturation, excuse me. So please try not to be too confused about all these f double primes, but they're all there for the reasons that I described earlier. The important thing is I have an equation of this type. The rate of change of size of a droplet has a 1 over r front factor, and then two pieces, one which is essentially the inverse of a critical radius which depends on the supersaturation, and 1 over r again. So let me just explain that in different terms. Keep that equation. So if I just plot this, it looks like that. There is a fixed point here, which is at r star of epsilon, and it's unstable. So if I start bigger than r star of epsilon, I will grow. And if I start smaller, I will shrink. So that's the key piece of physics you need for this droplet coarsening problem. But in equilibrium, at least, there's another way to think about this, which is also nice and is will come up again in the nucleation section in a minute. What I can do is I can say, well, what is the free energy of this droplet? I can calculate the free energy difference between the uniform state and the state with a droplet in for an equilibrium model. And that's U. And I can say, well, du by dr is some kind of force. And so I must be able to write that equation as some sort of mobility-like quantity of the r coordinate times the thermodynamic force on it. And indeed, U, we know what it is. In equilibrium, we know exactly what it is. There would just be a sigma here. And this object, as I mentioned, is the kind of bulk driving force. SD is the surface area of the unit sphere, and V is the volume. So I've just pulled that out. This is, pi's, 4 pi over 3, stuff like that. So I have the interfacial term after the d minus 1 bulk term here. And what I'm telling you is that this equation, which we derived without any thought of equilibrium, can be written that way. And indeed, if I do that, then I have constructed a potential for the free energy, or no longer free energy, of a droplet, which looks just like an equilibrium problem. Herbert.
Can I think intuitively about this diverging mobility, 1 over r to the d?
I will come back to that. So maybe you can ask me again when I come back to it. Okay. So we're lucky here in the sense that this equation, or that equation, has an unchanged form of mobility times gradient of a potential, and what's more, the potential, which could be anything in principle for an active system, is just like an equilibrium one up to this substitution of the correct choice of surface tension. Okay. So, now I want to talk about nucleation. So that was coarsening. That's the deterministic evolution of droplets. I have a critical radius which depends on the ambient supersaturation, which is ever decreasing. And small ones grow. Small ones shrink and large ones grow. Right, so if I had a passive problem of exactly the form I've described, the normal way you would do it is you just say, right, I know the landscape, I know the free energy landscape, so I know the height of the barrier, and the nucleation rate is proportional to the Boltzmann factor for being at the top of the barrier, because that's the hardest thing to do on the way to get over the barrier. So the nucleation rate up to some front factor, which I won't talk about today, is exponential minus barrier height over kT. That's the Boltzmann-Kramer's classical picture. And an alternative, which in equilibrium, of course, gives the same answer, is to say, well, okay, but let's think of R as a coordinate, and we know the deterministic motion of R, and what's more, we know how to factorize it into a thermodynamic force and a mobility, because I know separately what the potential is and what the R dot equation is. So I can figure out the mobility, and in equilibrium, that's completely unambiguous. And so then I know what noise I have to add here to a Langevin equation to get the Boltzmann statistics out of this equation here. Or, if you want, you can explicitly construct this Langevin equation. But you can see how to understand it from what I've said. There must be a form like this. That must be the deterministic equation, and the noise must match the mobility in the usual fluctuation dissipation sense. And the answer is this. So this, or more accurately perhaps the whole thing, is something I'm going to call the classical nucleation theory for model B. And what we're interested in is what's the classical nucleation theory for active model B plus? What's the analogous theory? And hopefully you'll already be able to guess it from what I've said. I can't just assert, oops, go back. Back, please. That's it. Now then, where was I? Here. I can't just use the Boltzmann distribution for the barrier height, but I can use the Langevin equation. And if I do, I notice that the only thing that has changed to that Langevin equation is the potential has changed by having the non-equilibrium interfacial tension stuck in it. And the important thing which enables me to do that is to say the noise term is unchanged. And that's because what is the mobility of R? Well, I have, and this is now answering Erwin's question, I have in my equation motion, I've got this droplet, there is a random term in the flux, which is just white noise. So I could, if I wanted to, just integrate that random variable over the surface of a droplet and figure out what is the mean volume flow or mean compositional flow across this notional surface. And then because it's a spherical droplet, it will just restore itself to circularity, constantly. So I can think of that M of R as just a Jacobian. And you can see, when you think that way, why it's got weird stuff like delta phi in, because a certain amount of random current of phi across the interface translates into an amount of random displacement of R that does depend on the width of the miscibility gap. And also the 1 over R is basically just saying, well, this is adding up a random variable over the surface of a sphere. I'm going to get less and less and less of it the bigger the sphere is. So that's why the mobility has the negative powers of R. Okay.
Sorry, Mike, why does it have all d powers rather than d minus 1, something you might imagine?
Yes, good question. I'm not sure.
Okay.
I'm sure I can figure that out, but not while I'm giving a talk.
Sure.
Okay. Right. So we know the answer. All I have to do is put the shifted barrier height into the usual Kramers-Boltzmann expression.
Isn't that quite brave, because you don't even know whether there's some kind of free energy function or interactive model?
So the thing which we have to assume is that the instanton, the pathway which connects me to the phase separated state, proceeds via a spherical droplet. Because if it does, there's only one coordinate. And if there's only one coordinate, even in an active system, I can construct a potential, because the gradient is in one dimension, everything's a gradient. But there's an interesting twist to that, which I'll come to in a second. So yes, and in general terms, it would be brave and it won't work, and I'll say that now. So for the scalar phi, for this idea of proceeding via a spherical nucleus, it's quasi-passive in the sense that I hope is obvious. Of course, we could not do that if the interfacial tension relevant to the droplet or bubble problem was negative, so we have nothing we can say in this perspective about the reverse Ostwald case. And yes, we're not expecting similar luck in other cases, so I say lucky rather than brave. Because in general, say, even if I put this problem in an external field, for instance, the critical droplet would not be spherical. So it would have more than one coordinate, and the shape of this droplet would have some non-trivial progress as I went across the barrier. So we have plans for these more general cases, but I'm not reporting any of that here. Even here, one feature of the equilibrium calculation, which is fundamentally follows from the principle of detailed balance, if you think about it, is that whatever way you go up the barrier, if you start at the top and go back the way you came, that's also the way you come down. So the most likely path of ascent to the top of a barrier is always the time reversal of the deterministic descent path. So another corollary of that, in this problem here, say I have a finite-sized volume. So I have two possible metastable, well, two stationary states. One which is homogeneous, one which has a big droplet in this volume. And I can ask, what's the path and the probability of going from the phase-separated state back to the homogeneous state? In an infinite system, it's 0. In a finite system, it's finite. And you can ask what the path is, and Zakin et al. Look at that, and it's different from, it is not the time reversal of the nucleation and growth process I've described. So we're even more lucky than we thought in that sense. Okay, and a word about coupling to fluid flow. Took me a long time to realize this. If you accept the premise of the classical nucleation theory, because the glowing droplet is radially symmetric, the fact that it may be coupled to an Navier-Stokes equation is irrelevant, because if the fluid flow is incompressible, you can't have a radially symmetric fluid flow, full stop. So the only way the fluid flow could matter is if somehow the critical nucleus breaks the symmetry, which in classical nucleation theory it doesn't. So there's a kind of free add-on, which is to say that, well, yeah, I think I'm right. Even yes, so if I had the same model, active model B plus, and I couple it in the most general way to an incompressible fluid flow, it will make no difference to this particular calculation. Right. Good. So I want to turn to the second story, which is a little unrelated, so it'd be good if there are questions on the first one to take them now, I think. Anything urgent? Okay. So now we're interested in what happens after you've nucleated some droplets, and they're then going to do this coarsening thing. This is the Ostwald process. And also, if you have a spinodal decomposition, so you end up with some scraggy, complicated, twisted domain structure, the late stages is when that is coarsening, and the driving force is reduction of the interfacial area. So big droplets growing, small ones shrinking is one way to do that. If I have a bicontinuous system, it's flattening out of curvature. So just to set the stage, so we had this equation before, so this is post-nucleation now. Large droplets grow, small ones shrink. It's easy to analyze that, at least at the scaling level. The average droplet size goes like t to the 1/3. The supersaturation decays like t to the minus 1/3, and nothing changes in that description from the passive case when I add the activity, except again for the substitution of interfacial tensions. If I have instead a spinodal process, I don't have nice spherical droplets. I still have the same scaling because essentially dimensional analysis gives me nothing else than this that I can get. So the average domain size of what may be ragged bicontinuous domains is still t to the 1/3. And that will also apply here. A slight twist, though, is that because the interfacial tension, as Cesare said, is different for a bubble from a droplet, then if I have a bicontinuous structure, it's got curvature of both sides on the same interface, and so there's some composite interfacial tension. And as Cesare said, for a flat interface, if you want to know about the capillary wave dynamics of that, you just take the average, but here you've got to have some rather more complicated average. But as long as both are finite, it will coarsen as if there was an interfacial tension, which is somewhere between the two, I think. Now, I should caveat that because if you look at the numerics on active phase separation, including these field theories, there's some suggestion that these exponents may be reduced. Now, it's very difficult to be sure about this because it's extremely difficult actually to get enough decades of L of t, particularly with a relatively small power like that, to say decisively that there's a change. The theory, as I've said on this slide, is no, there should not be. I will come back to that at the very end because there may be some explanation we can give of perhaps transiently why it looks a bit less. Maybe not. Okay. Now, so I want to turn. The characteristic length scale I've talked about, droplet size, domain size, lives in the peak of the structure factor. I'll show you some structure factors in a minute. I now want to turn to the low Q behavior, where it's been known that as time evolves, the low Q structure factor, which is describing the longest wavelength fluctuations at wavelengths much bigger than the domain size, goes like Q to the 4. And this goes back to the late 80s as an observation and, in part, an explanation. I would say an explanation as well. That's true for model B, passive, of course, and it's also true for model H. This is one of our own papers from the 90s, but there's other data as well. And that's true in model H, where there's a coupling to the fluid flow, which matters particularly in the spinodal domain, where you've got these ragged non-droplet structures. So there's a Q to the 4th hanging around here. Now, the first question is, why does it even vanish at low Q? And the physics of that is you start with some very small density and homogeneity, and the dynamics is conservative. So actually the limit of Q tends to 0 is stuck at whatever it was in the initial condition. And then you get this huge peak in the structure factor because the system is phase separating, so you get a massive density contrast, so you get huge amplitude in the correlation functions. So that's the reason that it's vanishing. But if you, at first pass, you say, well, okay, I have a vanishing function, no reason for it to be non-analytic, why not Q squared? So the question is really, why is it Q 4th and not Q squared? And that will be the rest of the talk. So, and there are plenty of lab experiments. Well, those don't look terribly convincing, but since then there have been more. Again, basically saying Q4, Q4, Q4 at low wave vector. And what you do is you usually scale these plots so that this peak in the structure factor in unscaled units is evolving in time to match the droplet size or the domain scale. Scale it by that, and you get a universal structure tends to emerge. Not always, and there are difficulties in 2 dimensions. We're now talking about the low Q part of that. So there's this word hyperuniformity. I think hyperuniformity is only half the number of syllables of vanishing structure factor at 0 wave vector, but that's all that it means, invented by Takata and Stillinger. But there is an industry in hyperuniformity, partly because in material science it's very interesting to have materials whose long-range density correlations are suppressed. And I won't go into the technological reasons for that, but they are of great interest to certain population of engineering types. So I think postdoc, maybe a student of Saltikato, who's the real driving force behind hyperuniformity, have looked at every model under the sun, including the Kahn-Hilliard equation, and here's your power fourth, which is quite a lot more convincing here, 4 decades, than the previous data I showed you. Okay, so there's a real thing there. And then the recent twist on this, which is last year, is that Löwen's group in Stuttgart published this interesting paper where they say, well, okay, so let's look at active versions. So they have model B, which they call Kahn-Hilliard, fine, and something they call extended Kahn-Hilliard, which has an extra current like this. They have the A and B, that's the extra current in active model B without the plus, and this is the zeta, so that's a lambda-like term, this is a zeta term, and they're all Q4th, no change. So whether you think that's deeply surprising is a matter of viewpoint, but it should at least be explicable. So what I'm going to do is explain it. So the basic argument for this goes back to Tomita, 1991, which is to look at the current. So that's the model B current, constant mobility, come back to that in a minute. So m equals 1 here. And here are my active terms. And even with the active terms, this current is the divergence of a second-rank tensor. And there's the second-rank tensor, if you're interested in it. So why should that matter? Well, it's intriguing, because it gives you a funny conservation law, which is usually not mentioned and not thought to be deeply fundamental, but is present in all of these models. Namely, if I define something which looks like this sort of, if I think of this excess composition relative to the mean as a density, this is the center of mass of that density. And this is conserved in the sense that its rate of change is phi dot here is div j, up to a sign at least. So that becomes a volume integral of j, which, if j is the divergence of a second-rank tensor, can be expressed as a surface integral. So, for instance, in periodic boundary conditions, say, I could get nothing here. P would be conserved. And in general, even if it just is controlled by boundary terms, we still say that it's conserved. Why should that matter? Well, we'll see that in a second. First, suppose S is analytic. So it looks like this, must be even. And we, as I said previously, start with a virtually uniform state so that initially S of Q at this T equals 0, yes, S are, yeah. So the whole of the structure factor is nearly 0. I just have an infinitesimal initial noise. That's the way I usually think of initializing a spinodal process, for instance. Then the Q equals 0 limit is conserved via the usual conservation law, namely that phi is the divergence over j. But interestingly, the second term here, which I can write as the two Q derivatives on this real space correlation function, is up to algebraic manipulations, it's this p squared. So that thing which is conserved sits here, that extra conservation all sits here. So that says that the second coefficient is also conserved if I have this form for the current. So since all the coefficients here start off negligible, what happens in the cases I've talked about is that this is basically stuck very close to 0, so is that. This has no constraint on it, and that's the one which gets big at low Q. That's the leading order growing term at low Q, and of course there's a peak at high Q, etc. So that's interesting. And as I say, that argument goes back to Tomita, but he certainly obviously didn't know about these extra bits in the current. Now, in general, I can go further, I can generalize. I should say, well, this could be one of those places where our models are a simplification too far. One has to be mindful. If you have a model which suddenly displays a conservation law that you were not conscious that the physical world should have, then you better worry a bit about your model. So we worry about the model. And there are various ways in which, so if I have this conserved object here, I can always write like that, and I'm left with whatever isn't, any extra current which is not of a div S form, I can consider. And where might such a current come from? Well, one is that if the mobility, which I set to 1, is a function of phi, I get an extra current which looks like that, so involving the phi derivative of m and this standard piece here. Noise is also such a current which cannot be written in that way. And so is the sort of mass flux term in model H. So these are all kind of up for grabs as to whether these are going to show Q fourth or Q squared. But as far as we know, they all show Q fourth. So when I say they show Q fourth, it is actually, I only need a weaker statement than that the second derivative of S at the origin is itself remains very small. All that matters by the time you do this plotting with the scale structure factor is that if it grows much, much more slowly than the peak in the structure factor, then by the time you've done your scaling plots, it's gone. So what matters is what's the first term in the kind of power series in wave vector that has a similar rate of growth to the peak of the structure factor. So the condition for that is actually here. So we're talking about little s, which is the scaled structure factor, and the exponent of 4 is true if the K2 coefficient of little s is vanishing if this object, which has got an extra L to the D, so this L to the D of 2 is helpful. As L gets big, it's easier to satisfy this condition. Okay, so how can we address this? Well, we have to look at that integral, which I just changed the color of. So there's this extra term, and we just have to ask how big is it? And we can estimate that, and it's easy to get bound. It's stochastic because it depends on the configuration, and I'll do the noise case in a minute. So I should be able to get a bound on P of t, and that gives me a bound on S. Okay, so noiseless cases first. So the ones I've talked about up to the slide before this, there is no such current, so it's done. The case of a variable mobility, I have to look at this curve, the statistics of this integral, and the arguments get quite delicate. It's in the paper that I referred to at the beginning, but the K4 does survive. The case I'll just go through, let me just show you those and then I'll talk about noise. So this is Filippo's data here, I think. And here's your Q to the 4th, and okay, it's the same notation as the Leuven paper had got, I think. Yeah. Right, so that's all looking healthy. Why did I draw that? Oh yes, that's model H, noiseless cases, there we are. So, sorry, I don't know why that was there. Right, so a case which is relatively straightforward, and it's actually very like what we were talking about earlier at the thinking about the random current at the surface of a droplet, is in the case of active model B, B+, passive model B, the noise current is just white, spatiotemporal white noise. And I have to integrate it over volume, which is the volume of the system, and it's extremely easy to do that, right? You just get the noise amplitude, some stuff, but the volume times the time. So then you can ask whether that thing, which now gives me a linear time scaling for S2 divided by the volume. So little s2, which is the scaled version, does decay for the known dynamical exponent of 3 for diffusive coarsening. So this is the way in which you can have terms that break the conservation law but don't break the K or Q behavior. Interestingly though, with noise here, K4 survives, but there is actually a crossover. So a time-dependent crossover, which means that the smallest K and or Q and okay, let me just show you the picture. So here you are. Again, so this is Filippo's data. So we have the Q4th, well-developed Q4th regime here, and this red line is showing that there's a crossover to a Q squared, and this red line is marching persistently to the left as time evolves, and is also moving to the left as I turn down the noise. So that's the way the pieces of this puzzle seem to fit together. So why might that matter? Well, one of the reasons that matters is there does seem to be some data out there declaring Q squared. There's this data on DNA nanostars, for example. It's not the only data in the literature, and they talk about Brownian motion of droplets. I mean, they're quite conscious of the fact that you can't get this from model B. What they do is they take a model B like this, and then they start adding extra diffusion of the droplets, which is on top of the model B diffusion that's already implicitly there from the noise terms. They get something more like Q squared. The other thing which is true, though, is that in active systems, generally, you do have lots of noise. And we've seen that again and again with the bubbly phase cases and so on. So a possibility is that if you're looking, say, at data from active particle simulations, you might see something a bit more like Q squared for quite a long time if there's somehow the noise is exaggerated in that case. Right. Conclusion. So, hopefully you'll be convinced after Cesari's talk and probably many other talks in this meeting that in general, once you start adding active terms to what would otherwise be diffusive or possibly coupled to fluids, phase separation type problems, everything does change. But luckily, there's some places where you can sort of more or less grab hold of the active case and merge it with what you know for the passive one and come up with some quantitative theory that is not, deeply altered by activity. So that was true with nucleation, where the only change was this interfacial one, and it seems to be true for the hyperuniformity thing as well. Somehow I didn't mention the coarsening. Well, yeah, I did at some stage say that there's some suggestion of shifted power laws, but I don't think, for me anyway, it's not strong enough to believe that they're ultimately different. I didn't mention finally, though, back to active model A. So the case where I have a fluid flow, then the extra current, the one which is not the divergence of something, is phi times V. So one can try to estimate the statistics of the integral of phi times V, and so far we haven't been able to show it's q to the fourth, but that could happen at any time. Or it may never happen. Thank you for your attention.
So what happens to the hidden conservation law when you encounter a non-reciprocal active system?
Oh, good question.
It looks like it's a momentum type of thing, so that motivates the question.
I see what you mean. Well, it looks like that, but I think it's pretty important that it isn't a momentum type of thing, because the momentum for me would be living in the model H bit, and this conservation law is a separate question from that. So, well, Christina, the smallest non-reciprocal diffusive model has 2 order parameters, and you have off-diffusive. Well, we should at least quickly check whether there is something like this in the flux equations. That's a good point. My guess is there isn't, but given that it was basically missed in the Kahn-Hiddy literature with the odd kind of delta function of Tomita. But by the way, I think this conservation law was largely forgotten because Tomita's original paper was incomprehensible and also technically incorrect. and so you can see why that would not be, wide attention to be paid to it. But the other little echo is that in hard condensed matter physics, there's a whole industry now of what's called fracton physics, which is where you have funny extra conservation laws, of which this is a perfectly good example, and one which they have studied, central mass conservation.
The fluid. Does active model H reduce, can you eliminate the flow and get back model B plus?
No.
Or not? You
No.
cannot. You cannot do that.
Well, it has the wrong coarsening law for a minute. So in the passive case, you can't. and it seems fairly obvious. So what happens in the passive case is that when you have bicontinuous domains, the pumping of fluid is a faster way of allowing the domains to grow than by diffusing the fluid.
Model B plus with no local kind of interaction. I mean, no local kind of.
Yeah, but we know that the model B plus still has the standard T to the 1/3 coarsening in the regime where the tensions are positive. Yeah. Yeah.
Sorry.
Yeah.
No, as soon as you put up that P equals integral of R phi, I was reminded of the dipole conserved models.
Yes.
But in those models, there's an actual separate local slow variable, right? In addition. Whereas here, somehow the conservation is assured by the fact that the current, I mean, the hydrodynamics of model B, or these others, doesn't have an additional new slow variable that we've all been missing all these decades, right?
No.
Whereas in the dipole conserved models, I guess there's actually a hydrodynamic associated with variables, right? I mean,
well, so the setting for this in the fracton community is things like you have, charges which can only move at conserved dipole moment.
Right,
so you have plus and minus charges, but they can a plus can only move to the right if a minus also moves to the left. No, the other way. So they move as a dipole, as a pair. Yeah. So then the thing which is conserved is actually an electrodipole moment.
Right.
So here's this strange thing, which is the mass moment of the phi field, which I agree is interesting because it's not independent of the phi field. It's just another attribute of the phi field. So somehow the same scalar field can obey more than one conservation law, which I agree is slightly, it's slightly dissonant, and I'm not quite sure how to think about it.
I mean, a more trivial example is in a fluid, you don't need a separate local field for angular momentum conservation because the symmetric stress does it. It's a little bit.
I think that's probably a better analogy. Yeah.
I'm still a bit puzzled about the M of R, the mobility.
Yes.
Because when you write it in the Langevin equation, it appears as the amplitude of the noise. So it looks as if, in your case, the amplitude of the noise, the variance of the noise, diverges with 1 over R to the D at small r.
Yes.
What I would expect is rather something with a noise amplitude because it's random on the on the periphery scales like power law in R instead of an inverse power law.
Okay, well, I've not thought about that. It's a good question, but I think the problem is that that Jacobian is always treating the interface as sharp and structureless. And if I really shrink that towards the origin, I run into the fact that actually it's some kind of tangent-like profile. And so...
It's not interface fluctuations.
No, it's not. It's not via capillary fluctuations. It's just random currents across a notional circular surface. I think. Maybe Cesare, perhaps Cesare may have something to add.
If it becomes smaller, I would guess that interface fluctuations should have some.
Yes, so it may be that there's a sort of paradox between the adoption of classical nucleation theory, in which the interface remains strictly spherical at all times, and the use of this mobility. So obviously what matters is what it's doing close to the barrier, and if you're really talking about the dynamics of a kind of micro droplet, then the precepts themselves will fail, and including presumably that calculation of m.
I also have a related question on the mobility, but the M of phi rather than M of R. Do you have a sense, maybe I might have missed, or didn't understand quite clearly, why in the cases, even when you have a density dependent mobility, you manage to get the Q to the 4th?
Well, I don't have a very good physical explanation. We can tell you about the calculation.
Okay.
But it's basically, you have, you've got this integral of J, and you basically say, well, inside this volume, there are patches of the correlation length. And then you have to basically sort of say, well, I can try and get a bound on this by assigning random values of phi, and so, yeah, so I still have a random variable with a certain correlation that I'm integrating over a volume. So then the discussion becomes a bit technical, actually, and you need to go further than I've just said, I think, in that case.
But presumably that relies that there should be some conditions on what the structure of M of phi is.
Yeah, so M is reasonable. I mean, so in terms of M, what we know is if you look at the coarsening behaviour, for instance, if you choose M to be sufficiently singular, so for instance it vanishes in one of the two phases, then you change everything. So when I was saying M, the extra current actually had an M prime of phi, we were doing a kind of small...
So if you do it in an infill?
I have no idea. Good question.
Okay, thanks again.
Thank you.